For a long time, the human mind needed a simple picture to understand the invisible. When scientists first began to explore the idea of atoms, they naturally borrowed images from the world they could already see. The most powerful and familiar structure was the solar system, with a central sun and planets moving around it in predictable paths. This image became the foundation of how people imagined atoms: a small, dense nucleus at the center, with electrons circling it like tiny planets. It was clean, logical, and easy to teach. However, this comforting picture, while historically useful, quietly planted one of the biggest misunderstandings in modern science. The solar system model of the atom did not emerge out of ignorance. It was born from early experimental success. When scientists discovered that atoms had a positively charged center and negatively charged electrons, it felt natural to imagine electrical attraction working like gravity. Early experiments seemed to support this view, and for a time, it helped scientists explain certain atomic behaviors. But as experimental tools improved and observations became more precise, cracks began to appear in this elegant model. The more closely scientists looked, the more the solar system picture began to collapse. One of the first problems was stability. According to classical physics, an electron moving in a circular path around a nucleus should continuously lose energy. As it loses energy, it should spiral inward and crash into the nucleus, destroying the atom. If atoms truly worked like miniature solar systems, they should be wildly unstable, collapsing almost instantly. Yet matter clearly exists. Atoms are remarkably stable, forming the foundations of all solids, liquids, gases, and living beings. This contradiction signaled that something fundamental was missing from the classical picture. Another issue emerged when scientists studied light emitted by atoms. When atoms are energized, they emit light at very specific wavelengths, producing sharp spectral lines rather than a continuous rainbow. The solar system model could not explain why electrons would emit only certain colors of light and not others. If electrons orbited freely like planets, their energy changes should be smooth and continuous. Instead, nature revealed strict rules, allowing only specific energy levels. This behavior hinted that electrons were not free, moving objects tracing smooth paths through space. As these mysteries deepened, scientists were forced to abandon the comfort of classical intuition. The atom was not behaving like a tiny version of familiar celestial systems. Instead, it was operating under entirely different rules. These rules belonged to a new framework of understanding that would later be called quantum mechanics. This shift was not just a correction of details. It was a complete transformation of how reality itself was understood at the smallest scales. Quantum mechanics introduced a radical idea. Particles like electrons do not have precise positions and velocities at the same time. Unlike planets, which follow clear paths that can be predicted far into the future, electrons exist in a state of uncertainty. This is not a limitation of measurement tools, but a fundamental feature of nature. The very concept of an electron following a well-defined orbit around a nucleus became meaningless. There was no hidden path waiting to be discovered. The path itself did not exist. Instead of orbits, quantum theory described electrons using mathematical wave functions. These wave functions do not tell us where an electron is, but where it is likely to be found. This probability-based description shattered the solar system analogy. Planets are always somewhere specific, even if we are not looking at them. Electrons, on the other hand, exist as a spread of possibilities until an interaction or measurement forces a specific outcome. The atom, therefore, is not a mechanical structure with moving parts, but a dynamic cloud of probabilities. The language of looking at an atom becomes misleading at this point. In everyday life, to look at something means to see its shape, boundaries, and motion. But atoms do not possess shape in the classical sense. Their appearance depends on probability distributions, energy states, and interactions. When scientists create images of atoms, they are not capturing a direct photograph. They are visualizing data, translating invisible mathematical information into something the human brain can process. These images are powerful tools, but they are not literal snapshots of reality. The persistence of the solar system image in popular culture has had unintended consequences. It has led many people to believe that science already understands atoms completely, and that the quantum world is simply a more detailed version of classical mechanics. In truth, the quantum world is fundamentally different. It does not scale down smoothly from our everyday experiences. The rules change, and intuition becomes unreliable. The atom is not a tiny machine operating under familiar laws. It is a system where the act of observation, probability, and energy are deeply intertwined. This misunderstanding also affects how people think about emptiness and solidity. In the solar system model, electrons are imagined as solid particles occupying definite locations, giving atoms a sense of structure. In reality, atoms are mostly empty space, with electrons spread out as probability clouds. When you touch a solid object, you are not feeling the contact of solid matter in the classical sense. You are experiencing electromagnetic interactions between electron clouds, governed by quantum rules. Solidity is an emergent illusion, not a fundamental property. The rejection of the solar system model also forces us to rethink motion itself. In classical physics, motion is continuous and smooth. Objects travel from one point to another along a path. In atoms, electrons transition between energy states without traveling through the space in between in any classical sense. These transitions are often described as quantum jumps, a term that reflects how foreign this behavior is to everyday understanding. There is no gradual spiral inward or outward, no orbit slowly expanding or shrinking. The old picture simply does not apply. Historically, letting go of the solar system model was not easy. Even some of the greatest scientists struggled with the implications of quantum theory. The idea that reality at its core is probabilistic rather than deterministic was deeply unsettling. It challenged centuries of scientific thinking built on predictability and cause and effect certainty. Yet experiment after experiment confirmed that the quantum description was not a philosophical preference, but a necessity imposed by nature itself. What makes this realization even more striking is how well the solar system model still works as a teaching shortcut. It is simple, visual, and memorable, but simplicity can be deceptive. While the model may help beginners grasp the idea of a nucleus and electrons, it must eventually be abandoned to avoid misunderstanding. Holding on to it for too long is like believing that a map is the territory. It can guide you initially, but it cannot capture the true complexity of the landscape. The atom, as revealed by quantum mechanics, is not something that can be fully imagined. It can only be described through mathematics, experiments, and carefully constructed interpretations. This does not mean the atom is unreal or unknowable. On the contrary, our understanding of it is incredibly precise and practical. But it requires a different way of thinking, one that accepts uncertainty as a fundamental feature rather than a flaw. By abandoning the solar system picture, science did not lose clarity, it gained depth. It opened the door to technologies that rely on quantum behavior, from transistors and lasers to medical imaging and quantum computing. None of these would function if electrons truly behaved like tiny planets. The success of modern technology is silent proof that the old image, however comforting, was incomplete. In the end, the realization that atoms do not resemble miniature solar systems teaches a deeper lesson about knowledge itself. Human intuition evolved to navigate a world of medium-sized objects moving at moderate speeds. It was never designed to grasp the behavior of the very small. When we insist on forcing familiar images onto unfamiliar realities, we risk misunderstanding the universe. True understanding sometimes requires letting go of pictures altogether and trusting abstract descriptions that feel strange but work with astonishing accuracy. The atom, then, is not a tiny clockwork model spinning in space. It is a subtle, probabilistic system that exists beyond direct visualization. Accepting this does not make the universe less beautiful, it makes it more profound. The failure of the solar system analogy is not a weakness of science, but a sign of its honesty. Science moves forward not by clinging to comfortable images, but by replacing them when reality demands something deeper, stranger, and far more fascinating. To understand the idea that electrons exist as probability clouds rather than fixed orbits, one must first let go of a deeply ingrained habit of thinking. Human perception is built around solid objects with clear positions. A stone lies on the ground, a bird flies through the sky, a planet moves along a predictable path. For most of history, science assumed that everything in the universe, no matter how small, followed the same basic logic. If something exists, it must be somewhere. If it moves, it must follow a path. This assumption feels so natural that questioning it seems almost absurd. Yet, at the scale of electrons, nature refuses to follow these familiar rules. Early atomic models imagined electrons as tiny charged particles orbiting the nucleus much like planets orbit the sun. This idea felt intuitive because it mirrored gravitational systems already well understood. However, as experiments grew more precise, this picture began to fail. Electrons did not behave like small balls moving along neat tracks. Instead, they exhibited behaviors that contradicted classical motion. They could interfere with themselves like waves, appear to pass through barriers, and occupy states that had no classical equivalent. These strange results forced scientists to reconsider what an electron truly is. Quantum mechanics introduced a radical shift in understanding. An electron is not simply a particle, nor is it purely a wave. It is something that can behave as both, depending on how it is observed. This dual nature makes it impossible to describe electrons using ordinary images. When scientists attempted to pinpoint an electron's exact position, the result was always uncertain. The more precisely they tried to locate it, the less certain they became about its motion. This was not due to faulty instruments or human error. It was a fundamental property of reality itself. Out of this realization emerged the concept of probability clouds. Instead of saying an electron is at a specific point, quantum mechanics describes the likelihood of finding it in various regions around the nucleus. These regions form patterns in space, often called orbitals. The term orbital is important because it deliberately avoids the word orbit. An orbit implies a path, a line traced through space over time. An orbital, by contrast, is a mathematical description of probability. It is a map of where the electron might be if a measurement were made. These probability clouds are not fuzzy, because the electron is blurry or poorly defined. They are fuzzy because the electron does not possess a single, definite position until it interacts with something. Between measurements, the electron exists in a spread-out state, described by a wave function. This wave function contains all the information that can be known about the electron, including the probabilities of finding it in different locations. The cloud-like appearance comes from plotting these probabilities, not from the electron physically smearing itself across space like mist. This idea deeply challenges classical realism. In everyday life, objects exist whether we observe them or not. A chair remains in the room even if the lights are off. With electrons, the situation is more subtle. The electron's properties are not fully defined until an interaction occurs. Before that, the electron exists as a set of possibilities rather than a single reality. This does not mean the electron is imaginary or unreal. It means that reality at this scale is fundamentally probabilistic. The shapes of these probability clouds are among the most striking features of atomic physics. Some are spherical, evenly spread around the nucleus. Others stretch into dumbbell shapes or more complex forms with lobes and nodes. These shapes arise from the mathematical solutions to the equations of quantum mechanics. They are not arbitrary or artistic interpretations. Each shape corresponds to a specific energy level and set of quantum properties. The diversity of these forms explains much of chemistry, including why atoms bond in particular ways and why molecules have specific shapes. What is especially important is that these clouds are not static objects. They represent dynamic possibilities. The electron's behavior is governed by energy, interactions, and external influences. When an atom absorbs or emits energy, the electron's probability distribution changes. The cloud reshapes itself according to new conditions. Yet at no point does the electron trace a classical path from one place to another. The transition happens at the level of probability, not motion in the usual sense. This concept also explains why atoms are mostly empty space. The nucleus occupies a tiny region at the center, while the probability clouds extend far beyond it. But emptiness here does not mean absence. These regions are filled with potential, governed by electromagnetic forces. When atoms come close to each other, their electron clouds interact. These interactions create the forces responsible for solidity, elasticity, and chemical bonding. What we experience as solid matter is the result of overlapping probability clouds repelling each other according to quantum rules. The probability cloud model also clarifies why electrons do not fall into the nucleus. In classical terms, a negatively charged electron should be attracted to the positively charged nucleus and collapse inward. Quantum mechanics prevents this collapse. The electron's wave, like nature, imposes constraints on how localized it can be. Forcing it into too small a region would require an enormous amount of energy. As a result, the electron naturally occupies stable probability distributions that keep it spread out around the nucleus. Stability arises not from motion along an orbit, but from the balance of quantum principles. Another profound implication of probability clouds is that electrons in atoms are indistinguishable from one another. In classical thinking, particles can be labeled and tracked individually. In quantum systems, electrons of the same type do not carry individual identities. They are described collectively by shared probability distributions. Swapping two electrons in an atom does not produce a new physical state. This indistinguishability plays a crucial role in the structure of matter and the behavior of materials. When scientists create images of electron clouds, they are visualizing abstract mathematics. These images often appear colorful and well-defined, but they are representations, not photographs. No camera can capture an electron cloud directly. The images are constructed from experimental data and theoretical models. They help humans understand patterns that would otherwise remain invisible. However, it is essential to remember that the real atom does not glow with colored shapes floating around a nucleus. Those visuals are tools for comprehension, not literal depictions. The idea of probability clouds also reshapes our understanding of causality. In classical physics, knowing the present allows precise prediction of the future. In the quantum world, even complete knowledge of the wave function yields only probabilities. We can predict the likelihood of finding an electron in a certain region, but not the exact outcome of a single measurement. This uncertainty is not due to ignorance. It is built into the structure of reality. Nature, at its smallest scale, does not commit to a single outcome until it must. This probabilistic nature does not weaken science. On the contrary, it strengthens it. Quantum predictions are among the most accurate ever made, matching experimental results to astonishing precision. The probability cloud model allows scientists to calculate atomic behavior with incredible success. It explains spectral lines, chemical reactions, electrical conductivity, and countless other phenomena. The fact that these predictions work so well demonstrates that probability is not a sign of failure, but a deeper level of order. Accepting electrons as probability clouds requires a shift in intuition. It means acknowledging that the universe is not obligated to make sense according to human expectations. The smallest components of matter do not behave like scaled-down versions of familiar objects. They follow their own logic, one that can be described mathematically but only partially visualized. This realization can be unsettling, but it is also profoundly liberating. It reveals a universe far richer and more subtle than previously imagined. At a deeper level, the probability cloud challenges the notion of objective reality as something fixed and observer, independent. While the underlying laws are objective, the outcomes are not predetermined in the classical sense. Each measurement brings one possibility into reality from among many. This does not mean consciousness creates reality, but it does mean interaction plays a crucial role. Reality at the quantum level is participatory rather than passive. In practical terms, the probability cloud model is not just an abstract idea. It is the foundation of modern technology. Semiconductors, lasers, magnetic storage, and quantum sensors all rely on the behavior of electrons described by probability distributions. Engineers design devices by manipulating these clouds through electric fields, magnetic fields, and material structures. The success of these technologies is a testament to the correctness of the quantum description. In the end, saying that electrons exist as probability clouds is not a poetic metaphor. It is a precise scientific statement about how nature works. The electron is not hiding on a tiny track, waiting to be discovered. It is genuinely spread out in a way that defies classical imagery. This spread is not vague or mysterious. It is governed by strict mathematical rules that can be tested and verified. Understanding this idea changes how we see matter itself. The world around us, which feels solid and definite, is built from components that are neither solid nor definite in the classical sense. Beneath the surface of everyday experience lies a realm where possibility outweighs certainty, and where existence itself is described in terms of likelihood. The electron, existing as a probability cloud, stands as one of the clearest reminders that reality is far stranger and far more fascinating than common sense ever suggested. There was a time when seeing was believing, when understanding the universe meant being able to picture it clearly in the mind. Science grew alongside human vision, relying on diagrams, models, and mechanical analogies to explain how nature works. Planets moved in visible paths, machines operated with visible parts, and forces acted through contact or clearly defined fields. In this world, certainty came from visualization. If something could be drawn, measured, and imagined as a physical object, it felt real. But as science moved deeper into the structure of matter, this reliance on visual certainty began to fail. Nowhere is this failure more profound than in the quantum description of atoms. At the atomic scale, nature refuses to be neatly visualized. The objects being studied are far smaller than wavelengths of visible light, making direct observation impossible. But the problem goes deeper than technological limits. Even in theory, atoms and their components do not possess definite shapes, paths, or positions in the way the human brain expects. The familiar language of pictures breaks down, and in its place emerges something far more abstract: mathematics as the primary language of reality. Quantum mechanics did not arise because scientists wanted to abandon visualization. It arose because every attempt to explain atomic behavior using classical images failed. Experiments repeatedly produced results that could not be reconciled with any clear physical picture. Electrons behaved like waves in some experiments and like particles in others. Energy appeared in discrete amounts rather than smooth flows. Measurement itself altered outcomes. No diagram could capture all of this at once. The only framework that worked was mathematical. In the quantum world, equations do not merely describe reality. They define what can be said about reality. Instead of asking where an electron is, quantum mechanics asks what can be known about its possible locations. Instead of drawing trajectories, it calculates probability distributions. The wave function, a central mathematical object in quantum theory, does not represent a physical wave moving through space like a water wave. It is a mathematical construct that encodes all the measurable information about a system. Its meaning lies not in how it looks, but in what it predicts. This shift marks a profound change in how knowledge itself is structured. In classical physics, mathematics supported visualization. Equations described motion that could also be imagined. In quantum mechanics, mathematics replaces visualization. The equations come first, and any image that follows is secondary, approximate, and often misleading. Scientists learn to trust the math even when it contradicts intuition. If the equations predict outcomes that experiments confirm, then the theory is accepted, regardless of how strange it seems. One of the most unsettling consequences of this shift is the loss of definite properties before measurement. In classical thinking, objects have attributes whether or not we observe them. A ball has a position and speed even if no one is watching. In quantum mechanics, certain properties do not have definite values until they are measured. This is not a philosophical opinion, but a mathematical result. The equations do not assign exact positions or velocities simultaneously. They assign probabilities. Visual certainty is replaced by statistical structure. Because of this, attempts to imagine what an atom looks like often lead to confusion. Any picture suggests a fixed arrangement of parts in space, but quantum mechanics tells us that such arrangements do not exist in a definite way. What exists are relationships defined by equations. The nucleus, electrons, and energy states are not tiny objects arranged like parts of a machine. They are components of a mathematical system whose behavior can only be expressed through abstract symbols and functions. Even the concept of space itself changes meaning at the quantum level. In everyday experience, space is a passive stage where events occur. Objects move through it, occupy positions within it, and follow paths across it. In quantum mechanics, space becomes part of the probabilistic description. Positions are not points occupied by particles, but variables in equations. The act of measuring position is an interaction that produces a result, not a revelation of a pre-existing fact. This reliance on mathematics over visualization has practical consequences for how science is done. Predictions in quantum mechanics are not about certainties, but about likelihoods. An experiment is repeated many times, and the results form patterns that match mathematical predictions. Individual outcomes may seem random, but the overall distribution follows precise rules. The success of these predictions demonstrates that understanding does not require a clear mental picture. It requires a correct mathematical framework. Historically, this transition was deeply uncomfortable. Many early pioneers of quantum theory struggled with the implications. They were trained in a tradition where physical intuition was central. The idea that reality could be fully described without being fully visualized felt incomplete or unsatisfying. Yet every attempt to restore classical imagery failed. The mathematics worked, the pictures did not. Over time, physicists learned to accept a new kind of understanding. Instead of asking how something looks, they ask how it behaves mathematically. Instead of demanding intuitive clarity, they demand predictive accuracy. This does not mean intuition disappears, but it changes form. Intuition becomes a feel for equations, symmetries, and abstract structures, rather than for physical shapes and motions. The mathematical nature of quantum mechanics also explains why different interpretations of the theory exist. The equations themselves are clear and unambiguous in their predictions. What they mean philosophically is less clear. Some interpretations emphasize probability as fundamental. Others suggest hidden structures or multiple outcomes. What unites them is that none can restore a simple visual picture without contradicting the mathematics. Reality at this level resists being turned into an image. This resistance highlights a deeper truth about human cognition. The brain evolved to navigate a world of moderate sizes and speeds. It excels at tracking objects, recognizing shapes, and predicting motion in familiar environments. It did not evolve to grasp the behavior of entities that do not have definite positions or trajectories. Mathematics becomes the bridge between human limitations and natural reality. It allows us to describe what we cannot imagine. In laboratories, this abstract understanding proves its worth daily. Scientists design experiments, materials, and technologies using equations rather than pictures. When engineers build semiconductors, they calculate energy bands and probability distributions. When chemists predict reactions, they use quantum calculations of electron behavior. The success of these efforts confirms that mathematical description is not a compromise. It is the most accurate representation available. The replacement of visual certainty with mathematical description does not make the quantum world vague or subjective. On the contrary, it makes it extraordinarily precise. Quantum theory produces predictions that match experiments to an accuracy unmatched by any other scientific framework. The uncertainty lies not in the laws, but in the outcomes of individual events. The structure governing those outcomes is exact. This distinction is crucial. Uncertainty in quantum mechanics is often misunderstood as ignorance. It is not that scientists do not know what electrons are doing. It is that the laws themselves do not specify single outcomes. They specify ranges and probabilities. This is a different kind of order, one that does not align with everyday expectations, but operates with remarkable consistency. As a result, the idea of reality itself subtly shifts. Reality is no longer a collection of definite properties evolving deterministically over time. It becomes a framework of potentialities governed by mathematical rules. What actually happens emerges through interaction and measurement. This view challenges classical notions of causality and predictability, but it does not undermine the reliability of science. It reframes it. When people ask for a simple explanation or a clear picture of an atom, they are often seeking reassurance that the universe remains familiar at its core. Quantum mechanics offers no such reassurance. Instead, it offers something more powerful, a way to understand nature as it truly is, even when it defies imagination. The price of this understanding is the abandonment of visual certainty, yet something is gained in return. By accepting mathematics as the primary language of the quantum world, science gains access to levels of reality that would otherwise remain hidden. The abstract symbols on a page correspond to real effects, real technologies, and real predictions. They describe a universe that is subtle, interconnected, and profoundly different from surface appearances. In this sense, quantum mechanics does not make reality less real. It makes it deeper. It reveals that what we perceive is only a thin layer of a much richer structure beneath. That structure cannot be fully captured by pictures, metaphors, or analogies. It can only be expressed through mathematics. The atom, then, is not something to be seen in the traditional sense. It is something to be calculated, inferred, and tested. Its true form lives in equations, not images. Accepting this does not mean giving up on understanding. It means embracing a different kind of understanding, one that values precision over familiarity and truth over comfort. In the end, the replacement of visual certainty with mathematical description marks one of the most important shifts in human thought. It teaches us that the universe is not obligated to match our intuition. It invites us to expand our idea of what it means to know something. And it reminds us that some of the most fundamental truths about reality are not visible to the eye, but are written in the language of mathematics, waiting to be understood by those willing to look beyond appearances. At first glance, observation seems like a passive act. We look at the world, and the world simply reveals itself. A mountain does not change because we observe it. A clock does not alter its ticking because someone watches it. For most of human experience, observation feels separate from reality, as though nature exists independently and our senses merely collect information about it. This assumption worked perfectly in everyday life and classical physics. But when scientists began to explore the atomic and subatomic world, this comfortable separation between observer and observed began to dissolve. In the quantum realm, observation is not passive. It is an interaction, and every interaction carries consequences. To observe something at an atomic scale, one must interact with it using energy, particles, or fields. There is no way to gently peek without touching. This unavoidable interaction lies at the heart of why observation changes behavior in the quantum world. It is not a mystical idea, nor does it depend on human consciousness. It is a physical fact rooted in how measurement works at very small scales. Consider what it means to observe an electron. Unlike a visible object, An electron cannot be seen directly. To detect it, scientists must use another particle or a field, such as a photon or an electromagnetic probe. When this probe interacts with the electron, energy is exchanged. That exchange alters the electron's state. The act of measurement does not merely reveal where the electron is. It helps determine where the electron ends up being found. Observation becomes part of the event itself. This realization shattered the classical idea that particles carry definite properties at all times. In quantum mechanics, certain properties exist only as possibilities until they are measured. Before observation, the electron is described by a wave function that encodes many potential outcomes. When a measurement occurs, one of these possibilities becomes real. This process is often called the collapse of the wave function, though the term is more a mathematical description than a physical mechanism. What makes this so unsettling is that the outcome cannot be predicted with certainty. Even with complete knowledge of the system, quantum mechanics allows only probabilities. Two identical experiments, prepared in exactly the same way, can produce different results. This randomness is not due to hidden variables we simply have not discovered. Decades of experiments suggest that the uncertainty is fundamental. Nature itself does not decide the outcome until observation forces a choice. This does not mean that reality depends on human awareness. The observer does not have to be a person. Any interaction that extracts information counts as an observation. A measuring device, a particle collision, or even the surrounding environment can play this role. Consciousness is not required. What matters is the interaction, not the intent. This distinction is crucial because it keeps quantum mechanics firmly grounded in physics rather than philosophy or mysticism. The idea that observation affects behavior becomes clearer through experiments. When electrons are fired one by one through a barrier with two openings, they create an interference pattern, a hallmark of wave behavior. But when scientists try to observe which opening each electron passes through, the interference pattern disappears. The mere attempt to gain information about the electron's path changes the outcome. The electron no longer behaves like a wave spread across possibilities. It behaves like a particle choosing a single route. This phenomenon reveals something profound. Information and physical behavior are deeply linked. Gaining information about a system changes the system. In the quantum world, there is no such thing as observation without consequence. The properties we measure are not simply uncovered. They are brought into being through interaction. Reality, at this scale, is not fully formed until it is probed. This challenges classical realism, the belief that objects possess definite properties independent of observation. Quantum mechanics suggests a subtler picture. The system evolves according to well-defined mathematical rules, but those rules describe probabilities, not certainties. The transition from possibility to actuality occurs through interaction. Observation is the bridge between the abstract mathematical description and the concrete outcome. The role of observation also reshapes our understanding of time. In classical physics, the future is determined by the past. If one knows the initial conditions and the laws, one can predict what will happen. In the quantum world, the future contains genuine alternatives. The past sets the probabilities, but not the result. When observation occurs, one alternative becomes the history that actually happened. The others simply never occur. This does not imply chaos or lack of order. Quantum mechanics is extraordinarily precise in predicting statistical outcomes. While individual events are unpredictable, large numbers of events follow exact patterns. the randomness exists within strict mathematical limits. Observation selects outcomes, but the range of possible outcomes is tightly constrained by the laws of physics. Another important consequence of observation affecting behavior is decoherence. In real-world systems, particles are constantly interacting with their environment. These interactions effectively act as continuous observations, suppressing quantum superpositions and making the world appear classical. This explains why everyday objects do not display obvious quantum behavior. Their quantum possibilities are rapidly reduced by countless interactions with the environment. Decoherence shows that the boundary between quantum and classical worlds is not fixed. It depends on isolation. The more isolated a system is, the more quantum behavior it can display. The more it interacts with its surroundings, the more classical it becomes. Observation, in this sense, is not a single event but an ongoing process that shapes how systems behave. Understanding the role of observation also clarifies why quantum mechanics feels counterintuitive. Human intuition is built around a world where observation has negligible impact. We are used to watching without influencing. In the quantum world, this assumption fails. Observation and influence are inseparable. Accepting this requires a shift in how we think about knowledge and reality. This shift has practical consequences. Quantum technologies deliberately exploit the relationship between observation and behavior. Quantum sensors achieve extreme sensitivity by controlling how measurement affects a system. Quantum computers rely on maintaining superpositions while carefully managing observation to extract results without destroying useful information too early. These technologies work precisely because scientists understand how observation changes quantum states. The observer effect also raises deep philosophical questions, but it does not undermine objectivity. The laws governing observation are universal and testable. Different observers performing the same measurement under the same conditions will obtain results that follow the same statistical patterns. Reality is not subjective in the sense of personal perception. It is probabilistic in a well-defined, shared way. At a deeper level, the role of observation forces us to rethink what it means for something to exist. In the quantum world, existence is not always about having definite properties. It is about having the potential to produce outcomes under interaction. Before measurement, a system is real, but its reality is expressed through possibilities rather than facts. Observation turns possibility into fact. This perspective does not diminish reality, it enriches it. It reveals a universe that is not rigidly predetermined but dynamically unfolding. The future is open within constraints. Outcomes are selected through interaction, not prewritten into the fabric of existence. This view challenges deterministic thinking but remains fully compatible with scientific rigor. When applied to atoms, this understanding changes how we interpret structure. An atom is not a tiny object with fixed components arranged in space. It is a system described by probabilities and interactions. The positions of electrons are not facts waiting to be discovered. They are outcomes waiting to be realized. Observation plays a role in shaping those outcomes. In everyday terms, this means that the microscopic world is not a static stage hidden beneath our senses. It is an active process, constantly negotiating between possibility and actuality. Observation is part of that process, not an external act imposed from outside. The observer and the observed are linked by the fundamental rules of nature. Accepting this does not require abandoning reason or embracing mystery for its own sake. It requires recognizing the limits of classical assumptions and adapting to a deeper framework. Quantum mechanics does not say that reality depends on belief. It says that reality at small scales is defined through interaction. Measurement is not just a window onto the world. It is one of the ways the world takes shape. In this sense, the quantum universe is not strange because it is illogical. It is strange because it does not match everyday experience. Yet it is governed by precise laws that have been tested countless times. Observation changes behavior not because nature is confused, but because interaction is fundamental. The atom, viewed through this lens, is no longer a passive object waiting to be seen. It is a living system of potentialities responding to every interaction. Observation does not reveal a pre-existing picture. It participates in creating the outcome. This realization marks one of the deepest insights of modern science, showing that at the foundation of matter, knowledge and existence are inseparably intertwined. Modern technology often feels magical, but its foundations rest quietly on the strange and counterintuitive behavior of atoms. Devices that fit into a pocket, machines that diagnose illness, and systems that transmit information across the planet all rely on principles that would have seemed impossible before the quantum nature of atoms was understood. This connection between abstract atomic theory and everyday technology reveals an important truth. Understanding the true nature of atoms is not merely an intellectual pursuit, but a practical necessity that shapes the modern world. At the heart of this connection lies the behavior of electrons in atoms. Classical physics could not explain why materials conduct electricity, why some act as insulators, or why others fall somewhere in between. The answer emerged only when electrons were understood as quantum entities with discrete energy levels and probability-based behavior. These ideas transformed physics from a descriptive science into a predictive and engineering-driven discipline. Once scientists understood how electrons occupy specific energy states and how they move between them, technology entered a new era. One of the clearest examples of this transformation is the semiconductor. Semiconductors are the backbone of all modern electronics, from smartphones and computers to satellites and medical equipment. Their functionality depends on the quantum structure of atoms within a crystal lattice. Electrons in these materials do not move freely as they do in metals, nor are they completely bound as in insulators. Instead, they occupy energy bands whose structure arises directly from quantum mechanics. By carefully introducing impurities into these materials, engineers control how electrons move, allowing currents to be switched on and off with astonishing precision. This ability to manipulate electron behavior would be impossible without a quantum understanding of atoms. Classical models cannot explain why adding a tiny amount of one element dramatically changes a material's electrical properties. Quantum theory explains this through changes in energy levels and electron probabilities. Every digital signal, every computation, and every memory operation ultimately traces back to electrons responding to quantum rules within atoms. Another profound application of atomic understanding is the laser. Lasers are so common today that they are often taken for granted, yet they are among the most purely quantum technologies ever developed. A laser works by forcing atoms into excited energy states, and then triggering them to release energy in a highly coordinated way. This process relies on the fact that atoms emit light at specific energies corresponding to transitions between quantum states. Without the concept of discrete energy levels, the laser would be impossible to explain or design. Lasers have transformed communication, medicine, manufacturing, and science itself. Fiber optic networks that carry vast amounts of data depend on laser light. Surgical procedures rely on lasers for precision and control. Industrial lasers cut and shape materials with accuracy no mechanical tool could match. All of this rests on a deep understanding of atomic behavior that defies classical intuition. Medical imaging provides another powerful example of quantum principles at work. Techniques such as magnetic resonance imaging rely on the quantum properties of atomic nuclei. The spins of these nuclei interact with magnetic fields in ways that are precisely described by quantum mechanics. By manipulating and measuring these interactions, doctors can produce detailed images of the human body without invasive procedures. What appears on a screen as a clear image of tissues and organs is, at its core, the result of atomics, scale quantum behavior translated into macroscopic information. Even the stability and diversity of materials depend on atomic quantum structure. Chemistry itself is governed by how electron clouds overlap and interact. The shapes of molecules, the strength of bonds, and the rates of chemical reactions all arise from quantum principles. Pharmaceuticals, plastics, alloys, and countless other materials are designed by exploiting these rules. Modern chemistry is not guesswork, it is applied quantum physics. The impact extends into energy production as well. Nuclear power is a direct application of atomic structure and the forces that hold nuclei together. Understanding why certain atoms release enormous amounts of energy when split required insights into nuclear structure far beyond classical physics. Even renewable energy technologies, such as solar cells, rely on quantum processes. When light strikes a solar cell, it excites electrons into higher energy states, allowing electrical energy to be harvested. This photoelectric effect was one of the earliest confirmations of quantum theory and remains central to clean energy technology. Perhaps most striking is how quantum understanding has reshaped computation itself. Traditional computers already rely on quantum effects in semiconductors, but emerging technologies push this reliance even further. Quantum computing seeks to use superposition and entanglement, properties rooted in atomics, scale behavior, to perform calculations beyond the reach of classical machines. While still in development, this technology promises breakthroughs in cryptography, materials science, and complex simulations. Its very possibility depends on accepting that atoms do not behave like classical objects. The success of these technologies demonstrates something important about scientific truth. The quantum description of atoms may feel abstract and unintuitive, but it works. It produces results that can be measured, engineered, and trusted. The devices built on these principles function reliably, often at scales and speeds that defy everyday understanding. This reliability shows that the strange rules governing atoms are not philosophical curiosities. They are accurate descriptions of reality. This realization also changes how we think about progress. Advances in technology are often portrayed as separate from fundamental science, but the two are deeply connected. Breakthroughs in atomic theory made entire industries possible. Conversely, technological tools enable deeper exploration of atomic behavior. This feedback loop drives scientific advancement forward. Understanding atoms leads to new tools, and new tools reveal deeper layers of atomic reality. There is also a cultural dimension to this story. Modern life depends on technologies that arise from concepts few people fully understand. This creates a gap between use and comprehension. Devices work flawlessly, yet their operation rests on ideas that challenge common sense. Recognizing this gap invites humility. It reminds us that reality is not obligated to align with intuition, and that human understanding progresses by embracing complexity rather than avoiding it. At a deeper level, the technological importance of atomic understanding reshapes how we define usefulness. Knowledge once considered purely theoretical has proven essential. When early physicists explored quantum mechanics, they were not trying to build smartphones or lasers. They were trying to understand nature. The fact that this understanding later revolutionized technology highlights the long-term value of curiosity-driven science. The atom, then, is not just a subject of textbooks or lectures. It is an active participant in daily life. Every message sent, every image captured, every calculation performed involves atomic interactions governed by quantum laws. The world around us is a vast network of atomic events coordinated through principles discovered only within the last century. Understanding this connection also reframes the idea of control. Humans do not control atoms by forcing them to behave classically. We control them by respecting their quantum nature and designing systems that work with it. Technology succeeds not by ignoring the strange behavior of atoms, but by harnessing it. This partnership between human ingenuity and natural law lies at the core of modern civilization. As technology continues to advance, this relationship will deepen. New materials, faster computation, and more precise medical tools will depend on ever more detailed knowledge of atomic behavior. The future of innovation is inseparable from the continued exploration of the quantum world. In reflecting on this, it becomes clear that the true appearance of an atom is less important than its behavior. We do not need to see atoms clearly to use them effectively. We need to understand the rules they follow. These rules, though abstract, have proven to be among the most powerful tools humanity has ever developed. The atom's quantum nature reminds us that reality operates on levels far removed from everyday experience. Yet those hidden levels shape everything we touch. Modern technology stands as living evidence that even the most counterintuitive truths can become practical foundations for progress. By embracing the true nature of atoms, science has not only expanded knowledge, but transformed the human world in ways once unimaginable.